Thanks, Steph, and thank you very much for the invitation. Delighted to be here. Really happy to see such a well-attended event, actually. So I've been looking at PFAS and PFAS replacements for the best part of 10 years, and we've seen significant growth in interest. And I think the presence of the audience, the size of the audience today illustrates that. So I'm going to give you a very quick run through the kind of things that we're doing at TWI, but also some of the areas that we're looking at and what we're interested in. And this is really because we are, as a research and development organisation, we're here to serve our members. We don't make materials, we help people, we support people, we support our industrial members across a whole range of different industries. So what I'm going to try to do today is to highlight some of the alternative materials that might already exist that could be potentially used in the applications of some of you and also others. It's worthwhile just having a quick review. We've seen some of these, I'm not going to spend an awful lot of time on them today. Why people use PFAS materials. Because PFAS is a generic term for, is it 10,000, is it 11,000, is it 12,000 different materials? Who knows? It used to be 4,700, it's only going to get bigger. They're all unique, they all do different things, and they're used by different people. But the supply chain itself is relatively small. We've heard about the size of the market, it's 28 billion euros. The fluoropolymers is Richard, 8 or 10 billion. I've got to say, I think I probably agree with those numbers. The smaller scale materials, the smaller scale molecules, 2/3 of the entire market, and those are the ones that provide risk. But that means that the supply chain itself provides a significant risk in terms of people using the fluoropolymers, which is what a lot of the conversations today are about. And where are they used? I'm going to focus on the coatings elements. Direct business risk, you can see business risk coming from many vectors. It isn't just about regulation. There's litigation, there is investor pressure, there is public pressure, there is profile pressure. There's also supply chain and the potential of supply chain shrinkage. If this 28 billion euro market shrinks because of the universal PFAS regulation, that will also have a direct effect on the fluoropolymers. So what are the alternatives out there? Because there is a business risk, and it's important for people to address that. It'll be different for each business, but they've got to be aware of all of the different vectors that might influence them. So there are emerging opportunities, and we've actually heard from some people here today who fit into this ecosystem, this landscape. Consulting services, we're looking at testing and analysis. But there's also people looking at alternatives, and that's really the direction I'm coming from, to support people to identify potential suppliers of products that might be widely available already, they've just not been used in these areas because they don't perform quite as well, or products and chemistries that have been widely available but have been focused elsewhere and could potentially be refocused with an existing mature supply chain. So the graph there is a graph that was presented at an event I was at in Riyadh at the end of last year. A company supplying polymer processing aids into the HDPE market. The bottom fell out of the world a few years ago, but they've replaced it. Polymer processing aids may be present in the materials that you use and you may not be aware of them. But the polymer processing aid market is starting to address the challenge of how do we replace materials that themselves may no longer be available or may become too costly because of regulatory pressure, because of investor pressure. So things are already starting to happen, we're already starting to see new materials come into the marketplace. The picture of Stanley Tucci, I didn't mean to, that was a picture of a cutout in the John Lewis department store in Leicester near to where I live, highlighting PFAS-free cookware. 10 years ago, most cookware was Teflon or PTFE based. 40% of the marketplace is now ceramic coatings. The world has already changed. The world is continuing to change. The alternatives are starting to get out there, and they may transit from cookware to other sectors and to other areas because the availability is becoming there. The pressure on the supply chain is being picked up by people seeing opportunities. sure many of you have seen this, but why siloxane? Why do we think siloxane is a useful area to go for? Well, actually, it's about bond strength, bond energy. It's also about the chemical group and the repellency. I come from a repellent world. Hydrophobicity, superhydrophobicity, how do you achieve that? Dig into that a little bit in a moment. But siloxane-based systems make an awful lot of sense in terms of direct replacements as a mature technology that can potentially be refocused. So the graph on the, or the table on the top left is similar to the some of the tables that Richard was showing on the right-hand side. So this is Ashby plots, and what I've put in here is some very simple terms, and we're looking at capability, operational capability of 170 degree plus. Well, fluoropolymers dominate. Some of them are also really quite expensive, so that might be a pressure to look at alternatives. The ones in red are non-fluoropolymer-based materials, and they are primarily, not exclusively, but primarily siloxane-based. Siloxanes can give us an awful lot of benefits and a lot of attractiveness. The chemical structures can actually be complex. If you think PFAS is complex, the siloxane world will blow your mind. It is extraordinarily complex chemically and structurally. And that's one of the things that can lead sometimes to challenge, and you'll see that in the next slide. Well, you can have siloxane-based coatings that have got very high temperature capability. They can be very hydrophobic, and they can also provide barrier properties. And the example at the bottom here is a stainless steel exhaust stack that is protected with a polysiloxane barrier coating to make sure that the stainless steel doesn't change colour when it gets to a high temperature. High temperature for stainless steel to change, 400 degrees C. Siloxane, polysiloxanes, in their broadest sense, have got an awful lot of capability, and I think it is an opportunity waiting for people to start to exploit and explore. And I know some of the manufacturers in the room are already starting to look at some of these things. We think in terms of complexity, so I'm just giving you a very quick overview here. No intention of going into any detail, happy to talk to people afterwards about that. But there's a whole range of different chemistries. Now, some siloxanes, and one of the things that is often said is, well, siloxanes can be hazardous. Some of them are SVHCs, and that's absolutely right. D4, D5C, D6, which fits into the D category. But actually, silica sand is also a siloxane, and that isn't hazardous. So there's a whole range of different materials, and being aware of the complexity of these allows you to navigate your way around, and that's one of the things that we're aiming to do and support our clients with. By the way, I'll also point out the title here. I've run out of page lab. I've lost count of the number of times people have told me they've got to put a silicone sealant around the bath, or they're going to use a silicone wafer in their electronics. Not quite true. Silicone is a metal. Silicone is a polymer. Silica is a ceramic. And there's a whole range of them that are intermediate as well, things like siloxanes. Happy to discuss all of those if anyone is interested. But moving on, you can see you've got different structures. Most of the PFAS polymers that you're looking at are linear in their inherent structure. You can have much more complex structures with siloxane-based systems, which can give rise to different sets of properties such as abrasion protection, hardness, wear resistance, chemical stability, as long as you're not at very high pH. I mentioned I come from a repellency background, so TWI is the most sensible materials joining technology. I've got 599 colleagues who are interested in joining things together. I'm the one who tries to prevent them from joining together. So you've got to understand why things do that. So adhesion is the reciprocal of adhesion. So quick graphs in terms of contact angle, because people always bring that up when you're talking in terms of hydrophobicity. Fluoropolymers, when there's no structure, tap out at about 120 degrees. If you want a higher contact angle than that, you've got to build in some roughness. And again, we've done quite a lot of work in the relationship between topography and chemistry in order to manipulate behaviours and repellences. There's an example here, a piece of stainless steel, which was grit blasted, coated with a very thin siloxane coating on the left-hand side, super hydrophobic. On the right-hand side, super hydrophilic because of the roughness. Management of material properties and behaviours comes down to an understanding of all of those key factors. We have looked at a number of siloxane-based systems in some case studies that we've done, primarily European funded projects, where we get in an increasing number of direct responsive projects. This is an example where we're looking at creating a super hydrophobic coating to improve heat exchanger properties. We're looking at mold release agents, transparent mold release agents, and I know some of the big siloxane companies are looking at LiDAR protection for your cars, for your automotive vehicles. How do you keep something transparent and clean when you're driving in dirty streets? So you can make sure things are clean. But it all comes down to adhesion, but it also comes down to things like mold release agents. Same kind of fundamental principles. How do you prevent things from adhering together time after time after time? Durability and performance. Those are the things we'll look at. We've also had a look at how you can replace commercially available materials with siloxane-based systems to provide ice repellents, particularly for the aerospace sector. And I see that starting to come through again in more detail now as people start looking towards things like EVTOL, where you've got to put protective coatings on composites. There aren't that many protective coatings available at the moment for composites. One of the areas that we're looking at. If you're going to use the material, you've got to have a selection process. As Richard was saying in terms of qualification, you've got to understand what the material is going to do, as well as being able to get hold of that. So you've got to have a selection protocol. This is an example of one that I've been developing for coatings for the marine sector for power generation, wind turbine, wave generation of power. This is an example of some of the results that we've been able to get. We can get very thin coatings, we can get reduced adhesion characteristics, we can get extremely good adhesion to a whole range of different substrates. We can change the roughness by the application of the coating if you get the application right. Planarizing the surface then makes it easier to detach things from the surface, so you can have the effects such as anti-icing or reduction potential of biofouling. There's a whole host of possibilities that can be done with materials that exist today for well-established supply chains. And again, just to illustrate, the contact angles we can achieve, we can regularly achieve the contact angles of 105 and 110 with siloxane-based systems, which rival, as hydrophobic, which rival PFAS-based materials. But it is also dependent on the processing that you go through. Summarising. There's a lot of opportunity. The world is changing. The world will continue to change, and the rate of change will increase. Siloxane-based materials, I believe, represent a really useful opportunity and capability for us to address some of the challenges. I'm not going to answer all of the questions. They're not going to solve all of the problems, but having clear sight of the materials that are available, we're just talking about peaks, siloxanes should be considered. It should be considered in terms of the broader context of siloxanes, not just as PDMSs. Increasing number of products being put into the marketplace. We've got a lot of experience in terms of identifying this and helping people to develop qualification protocols. We've also just launched a joint industry project, so we'll be happy to talk to anybody about potentially joining that. I'd just like to say thank you to some of my colleagues. There are contact details, and hopefully I've not been too far over this day.
Thank you very much. That was excellent. I think we have time for one quick question. I saw that hand first. I can answer.
Hi, Megan Seymour, Product Innovation. Great talk, Alan. Thanks. So you showed a quick blasted surface, I think, and mentioned also textural modulation through application methods. We're wondering if anyone has looked at kind of laser surface texturing for the texturing and then siloxane coatings and what you can achieve in terms of fibre fluidity pathway?
So it's a very good question. So we're looking at laser texturing for a whole range of different applications. So both in terms of surface cleaning and in terms of putting texture in there. The question that, when I'm in the chair like you are, the question I always ask is, what roughness is needed? That is the question that I think we don't have an answer to. We can see there's some clear influence of texture at a range of different hydrocarbons. And I recently had PhD students who produced a thesis on that, so I'd be happy to talk in more detail, but I'm afraid the answer is we don't know exactly what the key features are from a roughness perspective.
Thank you very much.